So we just finished the solution of the analytical analysis of the Couette flow with temperature gradient between the two plates. And I would like to follow on this example and do the same solution using numerical method. So again, I'm just listing the problem statement here. Two parallel plates. The lower one is fixed. The upper one is moving with a uniform velocity. We fixed the temperature of the lower plate to be T node. And we put the upper plate at a temperature T1. And it doesn't matter which one has a higher value than the other. So then after we simplified the continuity, momentum, and energy equation, we end up having from the momentum equation, from the continuity, partial u by partial x equals 0. That's the continuity. And for the momentum, we got partial u by partial y equal u over h, right? That's for the x momentum. And from the energy equation, we reached that partial 2t by partial y square equal minus mu over lambda. And the last term that left from the dissipation function is partial u by partial y square. So that's the energy equation. So if you refer back to the analytical solution, we show how to simplify that problem. Then we combine the terms. Partial u by partial y can be replaced by u over h. So partial 2t by partial y square is equal minus mu over lambda u square over h square. We multiplied by Cp and divided by Cp, the mu Cp over k, that's Prandtl number. So that's going to be minus Prandtl number u square over Cp h square. I just tried to make everything in a compact form. And this is totally a constant here, right? So that's a constant value. So now I end up having this governing equation. Now, this is the equation, and instead of solving that analytically, I would like to solve that numerically. We talked before about the Couette flow, and we agreed that the velocity change only was y direction, in the y direction, and the temperature also will change in the y direction. So I can simply take that any location between the two plates, and I can actually mesh it into a number of nodes, right? Say this is 1, 2, 3, 4. So now if I know the distance h, I can break down that so I can get my delta y. So each one of these element has a height of delta y. So let's call that this is a question I need to solve numerically. So far, we only fully aware of how to use the finite difference method. So we know that the second derivative of any function can be identified by fj plus 1 minus fj, this is 2, plus fj minus 1 divided by delta y square. That's the approximation of the finite difference central finite difference method for the second derivative. So what I can do, I can actually substitute into that left-hand side. So I will have t at j plus 1 minus 2 tj plus tj minus 1 divided by delta y square should equal to minus Prandtl number u square over Cp h square. I will bring delta y square to this side. So t of j plus 1 minus 2 tj plus tj minus 1 would equal minus the Prandtl number u square delta y square divided by Cp H squared. For simplicity, I'm going to call that term here A. Okay, so I'm going to call that A. Yeah, we can call it A. That's going to simplify things. So T, J plus 1. Remember, our target is actually Tj, right? So let's divide the equation by 2, right? And before we call that A, let me actually simplify the equation here. So Tj plus 1 minus, plus Tj minus 1, right? Plus PR U square delta Y square divided by Cp H square should equal to 2 Tj. Remember, this is the target temperature I'm looking for. This is the base point. I will divide by 2. So this will be 2, and this will be 2 in here. So this is what I'm going to call it actually A. Okay, so A is simply Prandtl number U square delta Y square divided by 2 CpH square. I'm trying to simplify the math as much as I can. So I can end up having the temperature of the node of interest is simply equal to 0.5 Tj plus 1 plus 0.5 Tj minus 1 plus A. And we know what is the value of A, whereas A is simply Prandtl number U square delta Y square divided by 2 Cp H square. So I can apply this equation at different nodes, and I can solve these. I can create the system of linear equations, and I can solve that. So let's go into more practical example here. So let's give numbers and get the sensation of the solution here. So the 2 plates are here. This is fixed. And let's assume that T node is equal 0 degrees C. I'm going to set up that temperature T1 to be 20 degrees C. I will set up this distance here to be 10 millimeter. I'm going to divide the domain into 5 segments. So that's node 1, node 2, node 3, node 4. So each segment here is delta Y is equal 2 millimeter. This is water. I can get the thermophysical property of that liquid here. So I can get the Cp, right? 4181. If I assume it's water, that's joule per kilogram Kelvin. That's easy. What about U? Let's assume U is 0.5 meter per second. U is equal 0.5 meter per second. I said H is 10 millimeter. So let's apply this nodal equation here and get the system of linear equations. So if I apply at node 1, what you're going to get? I'm going to get T1 equal to 0.5. Tj plus 1, this is the forward point. That's actually T2 plus 0.5 of Tj minus 1, which is times 0, plus A. And if I go for node 2, I can get T2 equal to 0.5, T next, which is T3, plus 0.5 of T before, that's T1, plus A. Then node 3, I would have T3 equal 0.5, T4 plus 0.5, T2 plus A. Then node 4, T4 equal 0.5. The forward is times 20 plus 0.5 T3 plus A. So this is the for nodal equations. I can arrange this equation in a matrix form. So if I put that in a matrix form, let's see what we have. I will try to make myself a little bit more organized here. So it's 1, 2, 3, 4. 1, 2, 3, and 4. I'm trying. So I'll take the first equation. I have T1, that's T1, T2, T3, and T4. So for the first equation, I have 1 T1, right? Then I will have minus 0.5 T2. I have 0 T3, and this 0, so the free term is going to be A. Then this will be 0. If I go for the second equation, I have minus 0.5 T1. Remember, you'll bring everything to this side here. T2, I have 1. And T3, I have 0.5 and 0 for T4. The free term will be also A. Go for the third equation. I have 0 T1. I have minus 0.5 T2. I have 1 T3. I have minus 0.5 of T4. And the free term is A. And the last equation, I have 0 T1, 0 T2, minus 0.5 of T3, and I have 1 T4, and I have the free term is 10 plus A. So now it depends on the value of A. Remember, A is Prandtl number, U square, delta Y square, divided by 2 CPH square. Let's assume that I picked something with A equals 0, a fluid of Prandtl number equals 0. So assume A is equal 0. If you put A equals 0, you end up having 0, 0, 0, and 10. Then you can solve that using MATLAB or any other iterative method. If I put A equals 0, I'm going to call that actually case 1. If A is equal 0, it's not because of the Prandtl number, but maybe the velocity of the upper plate is 0. That's maybe why it's causing everything is 0. CP has a value, H has a value, Prandtl has a value, delta Y has a value, but if the upper plate is fixed, right, A will be 0. If you do that, you will find that temperature will come as follow. You will have T1 is coming to be 4 degrees, T2 will be 8 degrees, T3 will be 12 degrees, T4 will be 16 degrees C. Does that make any sense for you? Yes, it does. Because it's everything is fixed. There is no motion. It's kind of simple conduction problem. Everything has to be linear, right? If there is no motion, it's a stationary fluid. It's conduction, and we know temperature distribution when there is no flow has a linear distribution. So I'm getting that linear distribution here. Okay. So what if case 2? If I have let's assume that we picked a fluid with a specific Prandtl number, 6.9. Then we have a velocity of a specific value, which is 0.5. So say that A came to be 0.8625. So if I double check that number, if I multiply the Prandtl number, 6.9, times U square, which is 0.5 times 0.5, times delta Y, which is 0.002, then I will divide that by 2. 4181, that's a CP for water, and I will divide that by H, which is 0.01 divided by 0.01 again. Yeah, so I got closed number. So let's assume this is your A, you got value for A, then you substitute into this equation. Now we are expecting that A has a value, which means that there is a velocity, so I'm expecting that distribution is not going to be linear. So from this, I got T1 equal to 7.45. I got T2 equal 13.175. I got T3 equal to 17.175. I got T4 equal to 19.45. Each one of them is degree C. You will see that there is big difference in the temperature distribution here. Then I did in an Excel sheet, I did different values of Prandtl number and Eckert number, and I looked to the temperature distribution, and I was able to show that we start with linear. If there is no motion or Prandtl Eckert is equal 0, then you really get that nicely parabolic profile based on that increased value of Prandtl times Eckert. That's Prandtl times Eckert number. Prandtl is fixed. Eckert, that include the velocity u square. So which means that increasing the value of Prandtl times Eckert means that you are increasing the velocity, which showing that how the profile is dragged with the flow. So I hope this example showing clearly how to use a numerical method to get the temperature distribution for a fluid flow between two plates. So I did use Excel trying to show if I change the combination of Prandtl and Eckert number. So for example, for the first case, it's already 0, so everything is stationary because of the Eckert number. Then I changed the combination to have that 2, so that's Prandtl times Eckert equals 0, that's equal 2, that's equal 5, and that's equal 11. It's clear that increasing the velocity is dragging the upper layer to move faster, and the transport of energy also increase with the kinetic energy here. So that's a combination here of different condition. Then I actually did the analytical solution. We have the final formula for the analytical solution, and I used that to confirm how close my numerical analysis to you. There's the formula for the analytical solution here. And you can use that to do the comparison with a numerical one, and it's really matching very well between the analytical solution and the numerical solution. So this is showing that it's much easier when you use numerical solution here compared to the analytical one, but we were able to use the finite difference method, at least for now, to get the same temperature distribution as the analytical solution as well. And that's include that example. For Couette flow with temperature included using the finite difference method.